Hello students, welcome back. In the previous class, we have done numericals from chapter 4. In today's class, we'll start a new chapter, that is torque on the current carrying loop or moving coil galvanometer. So in this chapter, we'll study about the mechanism of how a galvanometer works and how it is made. So in the first topic, we'll discuss about torque or a circular loop in a uniform magnetic field. So first of all, keep in your minds there is a uniform magnetic field. In the first diagram over here, diagram A, this white lines, it represents magnetic field B. Okay, it is uniform. And there is a current carrying loop. This loop PQRS. Okay, PQRS is a loop or a rectangular loop. So the side PQ is equals to RS, which will take as L, and the other two sides, that is QR, will be equals to SB, will take that side as B. So it is a rectangular loop. And over here, if you consider this side, what things will be perpendicular is PQ will be perpendicular to RS. Okay, in this diagram, PQ will be perpendicular to RS, which in turn is perpendicular to the magnetic field. Another thing, now the force. Force, when we have current over here, current is moving in clockwise direction, then force will be like in, over here what we can see is F2 is the force directing towards the camera, F1 is the force directing towards the board, F3 is upward and F4 is downward. This is the force in 4 different sides of a rectangular loop. So from here, using Fleming's left hand rule or thumb rule, F1 will be is equals to F2. Both forces are equal but opposite. F1 and F2 are equal but are opposite in direction, which is equals to I, B, L. This is the equation of the force we have studied in the previous chapter. Okay. F1 and F2 is equal to IPL, and we also know that F1 is perpendicular to F1 and F2 is perpendicular to the magnetic field. That is why we are writing IPL. We have removed the sin theta because sin 90 degrees is 1. So we are writing F1 is equals to F2. Now another thing what you have to remember is line of action, because for dipole moment what we have studied is for anything for dipole or to find the torque. Okay, over here we are going to find the torque. So for torque, one basic thing what we have to know is line of action of force. So F2 and F1 has got different line of action of force. If it has got the same line of action, then what happens? The force which are there in the opposite direction will get cancelled. Like suppose if force is applied on this stick in the two different directions, then the force will cancel each other because the line of action will be same. But if the line of action is different, then the force will be opposite in direction, but the line of action will be different, so it will not cancel each other, where else what will happen is the body will rotate. Okay, if the line of action is different, body will rotate. If the line of action is same, then the force will cancel out each other. So over here, for F1 and F2, what we know is, for F1 and F2 has different line of action of force. You can note it down, has got different line of action of force, whereas F3 and F4 has got same, equal and opposite and same line of action of force. So F3 and F4 are equal and it will get cancelled because they have got the same line of action. Force are equal and opposite in direction, whereas F1 and F2 has got different line of action, so it won't get cancelled. First thing to be remembered. I hope it is clear. Now what I have to find is, you have to find the torque of rotation of this force. This body will rotate, so I have to find the torque for this force. Now I hope this first one I can just remove it. Now I have drawn the same diagram like this. Now we don't need F3 and F4 because they are getting cancelled out. We only require F1 and F2. So if you see a loop from up, okay, then we consider the upper side of the loop to be like this. So this is the upper side of the loop like this. So this is F1 inward, F2 outward. Okay, just imagine this is a loop. F1 is inward and F2 is outward. So this side was considered to be B, and N and N dash. This N dash is the axis of the loop. N dash is the axis of the loop. And theta is the angle between magnetic field and this one, that is the length of that loop. Okay, theta is the angle between, axis and the magnetic field, not the length. Theta is the angle between axis and magnetic field. So, hope this is clear. Now we'll refer to this diagram for further derivation. Now, what we are going to find is, we are going to find the torque. Now, torque is force multiplied by perpendicular distance. Force we have already found out, F1 is equals to F2, both are equal, that is IVL. Now what you have to find is perpendicular distance. So from this diagram, what will be the perpendicular distance? Perpendicular distance is, when this rotates, the distance of this point to this point. So for this, when this part of the loop reaches over here, that will be the perpendicular distance. So for that, let us draw a triangle over here. Okay, this length will be the perpendicular distance. Now, if this angle over here is theta, then this angle will also be theta. This will be your 90 degree. Okay, so now we have got right angle triangle over here. So what will be this side? Now, this side will be your, if you are considering a base angle, then what you have to consider is, if you are considering angle over here, then you have got to consider sine theta. So this side will be your, this side of the loop will be B sine theta. So if this is theta, this side will be the base, this side will be the perpendicular. I just told base, this side is the perpendicular. So sine theta is equals to perpendicular divided by hypotenuse. So if this is theta, this side is perpendicular. Suppose if you are getting confused, let me start this again. Suppose this side is x. So it is perpendicular is x. Hypotenuse is this side, that is b. Okay. So if you cross multiply this, then b sine theta will be x. So this x will be your b sine theta. I hope now it is clear how we got this perpendicular distance, that is b sine theta. So the perpendicular distance becomes b sine theta. Now we can find torque, that is force. IVL cross perpendicular distance is b sine theta. Now we'll rearrange this I small b L b sine theta. Now do not get confused with this small b and capital B. Capital B is magnetic field, small b is that side. Now b and L. L is the length and b is the side. So if you multiply length and side, what we get is, if you multiply this, we get area. So it is IA b sine theta. This will be the amount of torque when a loop, rectangular loop, is kept in a uniform magnetic field. Now from this equation, what we can see is, this is not only applicable for any rectangular loop. This is applicable for any surface where we can find the area, like a circular, square, any sort of loop where the area can be found. In such situation, this torque is applicable. Okay, now let us discuss about in what situation will the torque be maximum and which situation the torque will be minimum. Suppose there are multiple number of loops in that rectangular PQRS. So if there are multiple number of n number of coils, so if there are n number of coils, then the torque will be NIAB sin theta. Okay, for this n number of coils. Now at what situation the torque will be maximum? It depends upon the angle, that is sin theta. Sin theta is 90 degree. 90 degree means this axis of the loop and this loop. If it is exactly perpendicular to each other, that is, loop is perpendicular to magnetic field, theta is 90 degree, the torque will be maximum, and that will be NIAB. This is the condition for maximum. And when the theta is 0 degree, this is perpendicular, okay, so your parallel is perpendicular. When your loop is parallel to magnetic field, then the theta becomes 0 degree, torque will be minimum, that will be 0. So when it is parallel, torque is 0. As on it rotates, the torque will increase, it becomes maximum at 90 degree, and when it comes again back to 0, torque again becomes 0. So as the coil rotates in the magnetic field, the torque will increase, then again decrease, then again increase. So it changes like that. Now there is another term where you should be clear about, that is magnetic dipole moment. I think this term we have studied in chemistry also. It is the similar magnetic dipole moment. Magnetic dipole moment. It is nothing but moment of a dipole in magnetic field. Okay, in magnetic field. It is denoted by small m, and the value of magnetic dipole moment is NIA. Where NIA is the magnetic dipole moment. It is given by this equation. So if you replace this over there in the torque becomes, if in this equation, if in place of NIA you write magnetic dipole moment, you can write it this way: M cross B. This will be in terms of magnetic dipole moment. One example of magnetic dipole moment is for hydrogen atom. When the electron rotates in its own axis, then it creates a magnetic dipole moment, and the value of that magnetic dipole moment for hydrogen atom is equals to 9.3 into 10 to the power minus 24 ampere per meter square. Ampere per meter square. So this will be the magnetic dipole moment of hydrogen atom. So remember this equation of magnetic dipole moment. It is motion of a charge in the presence of magnetic field. So in the next class we will discuss about moving coil galvanometer. There are two types of galvanometer. We will discuss about both the types of galvanometer and how it can be converted into voltmeter and ammeter as well. So this much for today. We will continue in the next class.